So we're talking about ionic bonds, and to make it all easy, take a moment, like tab over if you got a computer and pull up a periodic table. If you're working from a device that doesn't tab over very well, actually my best advice is to like print one up, but if you don't have a printer, I get that that's problematic. And I normally just keep a stack of periodic tables in the classroom because we use them every day. But we're going to reference that a lot. We're actually going to start off by doing it. So I want to get it all together. And are we ready? If you hit the participants button at the top of your screen, you should be able to pull up the thumbs up, thumbs down, faster, slower info. Yeah, somebody's ready. So we are going to figure out what the ionic charge of these guys are. And this is actually pretty straightforward. So we'll start off with strontium. Strontium is, well, it's an element. It's SR. And what we're going to do is we're going to look for where it is on the periodic table. Can you guys tell me what group number strontium is?
2.
Group 2.
Or 5, one of those two.
Oh man, no, like look at the periodic table. Let me know.
Yeah, I saw it's 2. It's because it goes down and there's so.
Yes, it is definitely 2.
Confused me for a second.
Well, when you said 5, you confused me. So we got our little periodic table thing with the stair step, and then the big old space in the middle, and then this other kind of. Wait, that was bad. Let me do that again. We've got kind of this block here, and then the noble gases on the end. So what we do is we're going to put our finger where we see strontium, which is, in group 2. And if I move it to the edge, I'm going to move it to the left. I'm going to go 1, 2. Once it gets off the edge, that's going to be how much charge it has. And if it goes to the left, that's positive. And metals are always positive, so we will say that its charge is a positive 2. Now we have the metal-non-metal division, which is like a weird stair-steppy line that I'm making kind of diagonal here. So there's some strange stuff in this section here, and these guys act all kinds of weird for us, but these rules are going to work so well for groups 1 and 2, and then definitely all the non-metals. And actually, the cheat code is group 1 has 1 plus on it, and group 2 has 2 pluses on it. And that's just if you put your hand on the periodic table, like if it's in group 1, it just moves over 1. The same thing going to the right is going to be trying to head toward the noble gases instead of off the edge. So where is tellurium? That's Te. I know we're looking now. Oh, people are dropping it in the chat.
16.
Yeah, group 16. So 16 is over here. And we're going to go from 16 to 17 to 18. When it hits 18, we call that good. So that's 2 jumps also, but it's going to the right. And if it goes to the right, that would be adding electrons. So that would be negative 2. What don't you get, JC? Because tellurium is sitting like over here. And up on top it says 16 up there. Or it might actually say 6A, depending on your periodic table. Did that make a little bit more sense for you? All right, well, we'll let you find the next one. Find nitrogen, that's N. And while JC is looking, we're all going to do this with that waterfall method where everybody types their answer into the chat, but we wait for a second. And what we want to know is what group is nitrogen in? So everybody type their answer in, and you
Do I
just,
answer now or do I wait?
well, you type your answer in, but we wait to hit enter.
Can't I just say it?
No, because we're doing this, we're getting everybody involved. This is how I get to give everybody points for
Oh,
participating, is everybody types in their answer.
oh.
I know.
Yeah, come on, Harvey, don't ruin it, bro.
All right, now
Come on now.
everybody hit enter. So JC, do you have a periodic table out? Well, get a periodic table, man. It'll make it way easier. So nitrogen is in 15. We'll walk that over. So you'll think 15 to 16 to 17, and then it hits the noble gases. That is 3 steps. And so that will be 3 minus right there. And that's if nitrogen got enough electrons to be, you know, like a noble gas, it would have to pick up 3 of them. So that's your noble team right there. Magnesium, what group is magnesium in? Well, I know how to spell it. What group is it in? It's like over here, man. Yeah. And group 1 and 2, they make this easy for us. It just takes 2 steps to the left to get in. Metals are positive. Things on the left are positive. So we'll say it's positive. Now the hardest part of this exercise is finding where selenium is. Can somebody like just put kind of an X next to where selenium kind of is on my terrible periodic table? Yeah, so what group is that guy? 16 is underneath oxygen. Anything that's in the oxygen group, that's going to be a 2 minus. So selenium gets to be 2 minus. There we are. And clear these guys out and go to the next page. Good news. There's no Apex this week. You could play as much Apex Legends as you want, man. But I did link some videos up on Teams for you. I want you guys to watch those before Wednesday. So, you know, today. I put them up over the weekend so you could get a head start, but I know about how likely that was. Give me any clarifying questions you have about today's work or about the videos. And today's work is for ionic compounds. The videos are for covalent molecules. So we have 2 different types of bonds, 2 different ways we have to kind of represent how they are. So here we go, talking about our compounds. No, covalent, not COVID. Compounds are a combination of at least two elements. When they go together, they act as a unit. The compound, the unit, is going to be different than the component parts. This is the example that I use all the time is salt, because I love salt. Isn't salt good? No, you guys don't like salt on your food? Maybe.
Salt's a little too spicy for me.
Oh, I could just barely hear that.
I said salt's a little too spicy for me.
Ah. Well, and too much salt will definitely give you hypertension or other problems. What is an absolute unit? I have no idea. Now, the salt itself is, relatively good tasting. We would die if we didn't have salt in our diets. But the two elements that make it up, sodium, literally explodes when you put it in water. And chlorine is a gas that if you breathed it, it would kill you.
You ever hydrate off of salt water?
I mean, as long as it's not 3.5% salt, you can hydrate off of it, yeah. JC, please stop drawing on the board. If you have something to say, you can say it out loud. Now, our compounds are a thing because of chemical bonds. The chemical bonds that we're talking about here, I mean, generically, it's the force that holds two atoms together. But when we're making ionic compounds, it is the result of gaining or losing electrons. We aren't sharing any in this case. Sharing is for the covalent compounds that we have. So we're not doing shared between today. Our ionic bonds will always form between a metal and a non-metal. Sodium chloride is the biggest example, but we got magnesium chloride as well. They don't all have to be chlorides, but chlorine is in the halogen group because it makes good salt. The ionic bonds form compounds, and keep saying that out loud till you get it, which stay together due to the electrostatic attraction between the cation and the anion. Now, what is fun to say out loud here is electrostatic. You guys should try that out right now.
Electrostatic.
See, doesn't that seem good?
Wow. I
No.
feel better.
Yeah. What about the rest of you? Anybody else want to give electrostatic a try? You don't have to turn your volume on. I'll just watch and see if you do it. Doesn't that kind of feel fun? Feel very smart saying that out loud? And go track down a younger sibling and say electrostatic at them. Now, the ionic compounds that we
That
make...
just sounds threatening, mister.
Well, it's only threatening if you're scuffing your feet on the carpet first and you give them some electrostatic energy. Anybody ever do that?
I want to do that to Javier. It'd be funny.
Oh,
What? Oh my god.
I will sit you two at different tables.
Nice.
So ionic compounds at room temperature and pressure usually make a crystalline solid. You can think about salt. Salt's a crystal. But most of the ionic compounds end up being crystals also. And they tend to be small crystals. They all form kind of like a white powder. It gets very difficult to keep track of which compound is which. Are you ready for another cringeworthy joke from Mr. Fleming?
No.
All right, I'll skip it then.
That was a joke. No, 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 no.
Wait. There's still a cringe-worthy joke coming, don't worry. Our chemical formula
I
shows
hate
the
this one.
kind and number of each atom. The small numbers, these small numbers written below a symbol are called subscripts. Subscript is just, small writing. And they show the number of each atom present. The metals, those are cations, are written first in the formula. And here is an OG meme for you. It's Chemistry
All right,
Cat.
you can go to the next slide,
There
mister.
it is. Yep, there it is.
You can go to the next slide, mister.
We found the funny.
So I just want to see if we can identify how many atoms there are of a thing if I ask you for it. So we're going to do this like the waterfall method, where I'm going to say, and we'll model the first one that's easy. I'll say like, hey, everybody, we're going to type in the number and we're going to wait a second to hit enter, but how many oxygens are in carbon dioxide? And when I say that, you all look and you see that little number 2 right there. So you type in 2, but you wait to hit enter until I say ready, set, go. And then you all hit enter and I see all these 2s in the chat box. Yeah, we remember how this works. So you guys want me to do easy ones or hard ones first? All right, so we'll do a little bit of both. Let's say how many nitrogens are in aluminum nitrate, which is in this guy. How many nitrogens do we have? And we'll all take a second in the alone zone there. And hit enter. Oh, and if you private message me, it kind of screws up my ability to chat a little bit. So we do want to make it public. And yeah, I knew this was going to be a confusing one. So we got some 1s, we got some 3s, and there's even a couple 9s. So I can see where we're going with this. But we've got the 3 outside the parentheses, just like in math. It affects everything inside the parentheses. So in this case, it affects the nitrogen there. It does not, this 3 that's over here does not count toward the nitrogen, only the one that's outside the parentheses. So there's 3 nitrogens in there, and there's actually 9 oxygens, because that would be 3 times 3. Let's go down to the next one. How many chlorines, that's Cl, do we have in carbon tetrachloride? I want to write that in. Yeah, that one's pretty easy. All right. How many magnesiums are in magnesium sulfate? And go ahead and hit enter on that one. Yeah. All right, we'll do the hard one. How many oxygens in manganese nitrate? And hit enter. So that's the tricky one. And remembering that remembering that you've got to distribute out the 7 into the 3 to get 21, that's, it'll do that. But you notice we either get things where it's like, well, there's there's like a little 4 sitting right there, and that goes on the oxygen, so it's super easy. Or like, how many hydrogens are in hydrochloric acid, guys? Yeah. So we got super easy, or we got, you know, some of them are totally weird. Like, now you got to look at it and think, all right, maybe I need the calculator for that. And that's how our math is going to go in chemistry, one way or the other. Now, I talked about these being the weird stuff, groups 3 through 12. Those are the metals in the middle, and actually all the stuff under the stair step on the periodic table also. These transition metals, that's what those guys are called, have a bunch of different charges. And it's confusing. Nobody has to memorize this. We will tell you. So it could be like chromium could be +2, +3, or +6, which is kind of crazy to keep track of. Iron could be +2 or +3. And we will notate which one is which because we'll say iron 2 when we talk about it. And we'll use Roman numerals to try to keep that straight. So that would be the +2 form of iron that we end up with.
What causes the various charges?
The transition metals are really big, like they have a lot of electron cloud space, and the nucleus, if you think about it, like you have your nucleus in the middle, and then you have like this weird, hang on, wrong shape, this weird kind of diffuse electron space out here. They have so many electrons just kind of way out to the side that somebody will come in and like yoink an electron here and one here, and it won't even notice that's your +2, but maybe it'll even lose a third one, so that's the +3. Chromium's so big you could strip 6 electrons off the outside before it cared too much. Now, if you ask why 2, 3, and not 4, 5, and then 6, I got no idea at all. If you guys don't want a virus on your computer, don't download that. There are 3 exceptions that you need to memorize. And it's not the number, because the number is easy to figure out, but you need to memorize which ones are the exceptions. And those are silver, zinc, and cadmium. The silver, zinc, and cadmium. If you look, silver is, what group is silver in? I'll listen to it if you tell me out loud what group silver is in.
16.
Mister, no, don't do
Isn't
it.
it 11?
Please. Just
It's
don't.
in 11, mister. It's in 11.
It is in group 11. What group is zinc in? It's right next door.
12.
And cadmium, where's that?
Is it our next door neighbor?
I mean, tell me what group.
It is in group 12.
If you see, we've got the 1, like if you take out 10, you've got 1, 2, and 2 there. So the numbers make sense. That part is kind of easy to keep track of. That it is silver, zinc, and cadmium, there's no easy way to remember that it is those 3 in specific. Oh, I got a song to share with you guys when we're done today, so let's keep it on track. What we're going to be doing in the beginning are binary ionic compounds. They're only made of 2, there we are, 2 elements. Our examples, again, sodium chloride, that's always the example. Magnesium fluoride is another one. It doesn't have to be, doesn't have to be any particular two, just that it's made of two. So even though this has, 3 total atoms, there's only 2 elements in it. And when we write binary ionic compounds, we're going to use the charges to write out the chemical formula. And this is a few steps. It's a little bit of a process. We're going to get it and get some practice on it. Step number 1, determine the charge of each ion. We did that already today. Step number 2, we're going to have this crisscross method that's going to swap the values from one guy to the other guy. You'll see that in a second. And then step 3 is reduce the subscripts to the lowest possible terms. So my worked example, magnesium and chlorine. We got magnesium and chlorine. Magnesium is in group 2, so it's got 2 pluses. And chlorine is a halogen right next to the noble gases, so it's going to have 1 minus. When we end up mixing them together, we will get the 2 from the magnesium and the 1 from the chlorine. The 2 will go to the chlorine side, the 1 will go to the magnesium side. We don't write out our 1s, and we've got MgCl2. This crisscross thing, you can kind of think like magnesium is 2 positive and chlorine is 1 negative. How many chlorines would it take to equal the electrical charge in 1 magnesium? You can just hold up some fingers on the screen. Yeah, that's it. So it's 2. So there's our 2 chlorines. Like the math behind this is pretty simple math. But also knowing that you do this crisscross applesauce thing, that's also kind of easy to work with. Now, I think most of us already know how to get the screen annotation stuff, but for the review, you go to the view options. You're going to click it and get annotate, and then you get this cool set of stuff. The text feature will allow you to write stuff out, and it looks much better than when I try to draw it. The only problem is you can't do subscripts or superscripts very well like that. Oh, Justin, I looked at your meme already. I even gave you a reaction for it. Yeah. Now, I want to give everybody a second to try to grab these tools. If you are working on an iPad, this is one of the cool things you've got with Zoom is you can just draw with your finger, which works way better. But if you're using a computer with a mouse, you'll draw like me where it looks like you're, yeah, that is totally real. We can see you. Yeah. And you will notice everybody's name shows up next to what they write. So if you draw something inappropriate, we all know it's you. I don't know if that's a good thing or not. Thank you, JC. And we will be doing this for the next part of class. So I'm clearing out the drawings so we can do the work. What we want to do is see what the formula for magnesium phosphate would be. Yeah, not everybody has the option to draw on it, so you can help out the group get done with this by throwing up some of the charges. Now, the charge of magnesium, we've been doing all day. That's 2+, that's easy enough. But what is the charge for a phosphate ion? So you find phosphorus on the periodic table, and then You have to count over to see what the charge is. JC, find the charge for phosphorus.
I'm afraid I cannot do that, sir.
All right, well, get a periodic table out instead of graffitiing up the board.
$15.
So it's group 15. How far away from the noble gases is that?
Oh, about like 1, 2, 3, 3.
So it's got a charge of, well, not 31. Come on, Fleming. That is
21
minus. There. With this, we then get the crisscross method, where you take the number from one side and put it to the other. And what I want you guys to do is, everybody give it a shot if you've got it, to write the chemical formula out in the area, like use all that space, take it up. But we've got the Mg2 plus, P3 minus, crisscross it over. And remember that capital letters count when we're doing all right, Melanie got it. Now, if you're doing the text, I would even change the font to be big and then do a small subscript number by hand. And that's kind of a pain in the rear, but it can work for us. Yep. Good work, guys. I'm going to bring up the next one. So I'm going to clear out the art. The next one is aluminum sulfide. Aluminum is tricky because aluminum is a metal, so it's going to be pluses, not minuses. But if finding the charge for aluminum seems hard, find it for sulfur first, and somebody write it up there. So we got 3 plus on aluminum. Thank you. It's on that. I'm going to put 3 plus. Maybe up here. Yeah, 3 plus. And what's the charge on sulfur? Two minus, excellent. So you're going to crisscross those guys, and what do you get at the end? Very good. You got a lot of Al2S3 going on. Now, one of the ways that we remember that aluminum is a positive ion is that we all know aluminum is a metal. And metals are always going to make cations. And cations are what?
Negatively charged ions.
No, they're positive.
Oh,
Did you see the cringy meme? Because I can go back, Jeremiah.
I saw it. I don't need to see it again. It's too.
They do have some with onions for anions, and I just can't get behind the onion thing. All right, should I let you guys have some time in the alone zone to work on the next one individually? All righty. We have silver and chlorine. Do you guys remember what silver's charge was?
+1.
All right, so somebody remembers. So we can make silver chloride then. I'm covering up my view of the board so I don't kibitz any of you guys at all. So go ahead and write your answer out. We feel like we're good on the answer? Let me take a look at what we've got. Ah, excellent. Yeah. If you don't have to write any numbers, you can just use the text. It's pretty good. Excellent, excellent. A lot of AgCl. And that's something we actually work with in the lab. Potassium iodide. You guys have all heard my terrible potassium joke already.
Mister, tell us another joke.
But you heard about me asking the girl out.
What girl? Who?
I mean, this is my old lab partner back in the day.
Who?
Well, I'm protecting the innocent by not naming names, JC.
Innocent?
Yep.
Who's innocent?
Her
No one.
business.
Oh,
Certainly
man.
not you, young man.
Purple is not the imposter.
So yeah, you guys just look up the charge of potassium and iodine, figure out what it is. And you know what potassium iodide is used for? Oh, you're not writing your answers? Dear Lord, guys. I'm covering it up and giving you a moment. This is for all the enchiladas. Very good work. Now, do you know what potassium iodide is good for?
I don't.
If you take potassium iodide, you will not get radioactive poisoning.
Mister, you want me to unmute?
Is that like a type of drink? What do you
It's like a
I
pill,
should drink it? Oh,
but if there's radiation in the atmosphere, you're supposed to take it, and your thyroid won't uptake radioactive particles then. Next one on the list is zinc phosphate. And I say next one, but that's the last one. Zinc was one of our special cases. I can give you the secret there. Good, good. And you will notice it is not a coincidence really that we tend to get compounds forming on a 1-to-1, 2-to-1, or 3-to-2 basis more than anything else. And that's just, we're looking for the most stability out of all of these things. And if you get something that's a little unstable, the second another molecule or compound comes close to it, they'll just take parts out that don't fit so well, put other parts in, and everything will move on from there. So we get a lot of stability with the really low number ratios. If you ever do a problem and it comes out as like 7 and 15 for an ionic compound, we may have done something terribly wrong. Now, what questions do you guys have for me about writing our ionic compounds? Are you ready for a test based on it?
is it going to be a poll?
Well, I'll just give you a quick quiz. I mean, and if you're not ready for a test, this is where the homework to ask a clarifying question comes up. Because I find that these processes, they're pretty simple. You just go straight down the line. Remembering the process is what is hard.
Do you always take both numbers? Like they never cancel each other out, right? So you always just like switch them, right?
Yeah, for ionic compounds, you always switch them. So somebody asked how we got that 3 for zinc. So I'm going to clear all the drawings. And I'm going to write this out in big letters so that I can do small letters. But I've got Zn and P. And then we'll go down a little bit. Z, N, P. There. So zinc, being one of our special metals, we know that its charge is always 2+. And you guys who found phosphorus, that's underneath nitrogen on the periodic table, correct? Yeah. Yeah, don't be afraid to speak up, especially when I'm writing on the board. I can only see like 3 faces at once, but if it's in nitrogen's row, those are 3 minus on the charge. Now, to get these charges equal, like if I've got zinc and phosphorus and I want them to balance out, I could get, I mean, how could I make 2+ and 3 minus equals 0? Like if I do that, now I'm at 1 minus. If I get a second zinc, then I'm at 1+. So then I get another phosphorus and I'm at 2 minus. And so you like keep adding 1 on each side and seeing if it works. But the math is such that you can just take the number itself, wrong color, take the number itself and move it across into the other guy's space, across into the other guy's space. And then you're going to get zinc 3, phosphorus 2 on that. But what that is really saying in like a textual way is it takes 3 zinc to electronically balance 2 phosphorus. Oh, that's some excellent spelling I did there, isn't it? And we will go over all of this in rapid fire again. This is being recorded, so we'll have it up on the YouTube channel. And did that answer the question about how we got that 3 there? All right.